person who is affiliated in Austria, so Karlheinz Groechenig from the University of Vienna. His title is Total Positive Functions in Sampling Theory and Time-Frequency. Please.
Good morning. It's a great pleasure to be here. These research institutes are somehow oases in our lives where we can settle down for a moment and not be busy. At least I handle it like that, and I answer email just occasionally this week, so that's great. So this is a program on sampling, approximation, compression. I will talk about sampling. Sinan yesterday in his beautiful lecture already said we need sampling theorems, and I will show you how sampling theorems arise where totally positive functions play an important role. I should say this is joint work with José Luis Romero from Vienna and Joachim Stöckler in Dortmund. Basic ingredients are totally positive functions. I will deal with function spaces that arise from totally positive functions by taking subspaces of integer shifts. As an application, I'll say a little bit about Gabor frames, and there's at least one mathematical argument that I want to show you that involves, say, textbook complex analysis. So, sampling essentially is the problem we're given data, a value yj at a point xj, and you want to find, or nowadays you say learn a function f that basically reproduces these data, and at least when you have a model in the background, what you frequently do is that you take a generating function phi and assume that function you want to reconstruct is in the linear span of shifts of that function phi. Now, when you look at the recovery, so given the samples, you want to know the coefficients and then you know the function. When you evaluate at xj, what's behind is this matrix phi evaluated at the difference xj minus yk, and well, in order to recover, you need this matrix to invertible. That's what's often done in radial basis functions, where you do that in high dimensions and often with a Gaussian. So, well, now we just take this requirement as a definition, and well, instead of saying invertible, we say determinant is positive. So this is the main underlying object, totally positive function. So a function phi on the real line is totally positive if for any two finite sequences arranged by magnitude, so x1 less than x2 less than xn, and possibly different sequence y1 up to yn, the determinant of this matrix is non-negative. Okay, there might be equality, but usually it's greater than 0, so that matrix then will be invertible. That's an old topic in approximation theory. Actually, could already say ancient topic, was quite important in this development of spline theory, 1950 to 80. From what I know, it's still interesting in statistics, and I think it's still interesting, and what I want to show you is how totally positive functions are useful in sampling and shift-invariant spaces and in time-frequency analysis. So this is a motivation. This is the motivation for why totally positive functions arise. So let's just look at some examples so that you see this. This is an amazing condition, and it's kind of surprising that it even holds true for arbitrary sets of samples yj and shifts xj and shifts yk. But this you can work out by hand. The one-sided exponential is totally positive. The symmetric exponential is totally positive. So these are standard functions. This was very useful in spline theory. So monomial times one-sided exponential is totally positive. If you convolve one-sided exponentials, you can show that these are totally positive, and you can work out an explicit formula if you want. It's not very enlightening, but you get many examples this way. So, fundamental example is the Gaussian. That's again, I think it's an exercise in the book of Hardy, Littlewood, and Polya. The hyperbolic secant is totally positive, and this bizarre function here, exponential ax minus b e to the x for a b positive parameters, is also totally positive. It's probably not so obvious. Okay, so these are some familiar functions that are familiar to all of us, but of course there is a, you want to understand totally positive functions better, and there's a very beautiful characterization of Isaac Schoenberg. He characterized totally positive functions by factorization of their Fourier transform. I assume integrable, otherwise you could take arbitrary exponential. So an integrable totally positive function must possess this factorization. So let's look at that a bit more in detail. So the Fourier transform will contain a Gaussian and will contain a finite or infinite product of inverse linear functions. What's important is that the new j's are real valued. This means these functions have poles on the imaginary axis. So this may be a finite product. If you take an infinite product, then you first of all need that the parameters nu j are square summable, and then you also need these convergence factors, which we know from Weierstrass products. So where does this come from? Basically, if you take the one-sided exponential, then its Fourier transform is just this here. So essentially, totally positive means convolution of Gaussian with one-sided exponential functions. So for later purposes, I would call totally positive functions of finite type if this product is finite, Gaussian type if the Gaussian appears and the product is finite, and infinite type if the product is infinite, is an infinite product. So now let's go to the model for the functions we want to sample, and we call them shift-invariant spaces. In engineering, they're often called spaces of finite rate of innovation, spline-type spaces. It's what Feichtinger calls them. And the parameter is a generating function. For us, that will be a totally positive function. And then you look at all linear combinations of integer shifts, linear combinations with L2 functions, and that's the shift-invariant space with generator phi. So basic assumption is that the translates are stable. That's an easy condition to satisfy. We assume that, and for functions with some decay and smoothness, that's always satisfied. So the basic example is when you take phi to be sine pi x over pi x, the cardinal sign, because, well, the Fourier transform of this is characteristic function of -1, 1, and so the generated shift-invariant space is just the space of band-limited functions of bandwidth 1, and essentially that's you see that by cardinal series. The integer shifts form an orthonormal basis, and the Shannon-Whittaker-Kotelnikov sampling theorem tells you that you can describe exactly all these functions. Now, why do we care for more general examples than band-limited functions? Well, take Fourier transform of a function in shift-invariant space, then you get phi hat times a periodic function that's locally in L2. So if phi hat has some decay, you could say these functions are approximately band-limited. If phi has some decay, then these functions possess some localization. The corresponding series will converge fast. So you can combine band-limitedness and localization in one object, these functions. So these are the spaces in which we are going to sample. And so what is a sampling theorem? A sampling theorem is essentially an inequality like this. You take a set X, you take the samples of F on this set X, take the discrete L2 norm, and the discrete L2 norm should be comparable, equivalent to L2 norm of F with uniform constants for all F in the shift-invariant space. So these constants, positive, are the sampling constants, and the ratio B over A is in a way the condition number. Now there are many aspects that we could look at: approximation, interpolation, localization, algorithms, numerical issues. But what you see is if F vanishes at all sampling points, that F must be 0. The fact that you have this lower inequality implies some stability. So small changes of the samples imply small changes in F. This is a rigorous definition for that. And once you have a sampling inequality, this implies automatically certain reconstruction algorithms. You go to frame theory, calculate a dual frame, or iterate, or whatever. So once you have such a theorem, these questions basically have been answered. So fundamental question is how to determine when a set X is a set of sampling for a shift-invariant space. One issue is, well, obviously you need sufficiently many samples, and how many? Well, the question is how you measure that. For this talk, I will choose the Beurling density. So you count the number of sampling points in every interval of length r, take the smallest of these numbers, divide by the length of the interval, and then let r go to infinity. So this is basically the average number of samples per unit length. So let me briefly mention what is known, and the prototype of all sampling theorems in its realm is the sampling of band-limited functions. So the Fourier transform of the L2 function is supported on an interval of length 1. And the main theorems go back to Beurling and Landau. So the first one is a sufficient condition. If the lower Beurling density is strictly greater than 1, and X is separated, so there's a minimal distance between points, then X is a set of stable sampling. In other words, you have such an inequality hold for all band-limited functions. There is a necessary condition. It's also expressed in terms of the Beurling density. If you have such a sampling inequality for X, then you must have Beurling density greater than or equal to 1. So this, in modern language, we cannot. So the density, Beurling density, just measures how much information you need to obtain a sampling theorem. So stability and this amount of information are almost equivalent. What happens at the critical density is a very subtle issue, and one person in the audience Kim Ortega-Cerda knows everything about that. Okay, so proof is essentially with complex analysis and weak type limits, a method that Beurling developed. The proof of the necessary condition is, was with operator theory, but I should point out that there is a, I would say, there's a very short proof, 1.5 pages, and the world record for the shortest proof is due to Sasha Olievsky and Nitzan Shahaf. So they have simplified Landau's proof in a way that you have chances to generalize that, and Landau's proof is, I still find, very hard, but it gives more information. Okay, so now let's go to shift-invariant spaces. So a mild condition on a generator is sufficient to give us the same necessary condition. So if I look at sampling sets in shift-invariant space, then lower Beurling density greater than 1 is again a necessary condition. For the last time, I recall that sampling theorem amounts to sampled L2 norm is equivalent to L2 norm for all f in the function space. Okay, so far so good. It's somehow intuitive. If you take integer shifts, you should have at least one sample per unit interval, and that's roughly this condition. So sufficient conditions, there the story becomes more difficult. There is a qualitative version. It's already more than 20 years old by Akram Al-Rubi and Hans Feichtinger. Both are or were here. Again, small decay condition that you have seen as an amalgam space in Hans Feichtinger's talk. And so basically the statement is if you sample densely enough, then you get a stable set of stable sampling. Now here, the densely enough means that you measure the maximum gap between two samples. In higher dimensions that would be called a mesh size. And so if the maximum gap is small enough, that depends on the generator. What small enough means, if the maximum gap is less than some delta naught, then you get a set of stable sampling. Now, that's fine. It sort of tells us, in principle, if we sample densely enough, then we get sampling. But if you look at that, you have, well, if the maximum gap is delta, then you get about approximately 1 over delta naught samples per unit interval. So this is quite far from, unless you have good estimates on the maximum gap, this amounts to possibly huge oversampling. So this is basically a qualitative result. Quantitative results are much more rare, and so maximum gap strictly less than 1 implies stable sampling. So 1 is the best possible maximum gap that you can expect. So with this kind of density definition, there are a few cases where you can get the optimal result in terms of the maximum gap. These are familiar objects in approximation theory. The generator might be a B-spline, so a convolution of a characteristic function, m plus 1 times. It might be an exponential B-spline, so that's a variation where you multiply each characteristic function by some exponential function. The lambda j's are some real-valued parameters. And thirdly, a finite product of these inverse linear factors. In view of the characterization of totally positive functions before, you recognize that this would be phi would be a totally positive function of finite type. So for a very small class of generators, there is an optimal result in terms of the maximum gap. You cannot do better than the one here. Okay, so these are results that go back, well, you see, we already dealt with that in 2000. It's a recurring theme because there are so few optimal results. Now, the next result is rather recent, and it's about generators that are totally positive functions where the Gaussian appears in the factorization. So we take phi to have the following form: the Fourier transform factors into a Gaussian and a finite product of these inverse linear factors. So totally positive of Gaussian time. Then we could show that if the lower Beurling density is strictly greater than 1, then X must be a set of stable sampling. I'm still very happy with this result. First of all, it mimics perfectly the situation of bandlimited functions. Beurling density greater than or equal to 1 is necessary, and strict inequality here makes it sufficient. And there are only, I think, three examples of such theorems. One is the one for bandlimited functions, dimension 1. The other example is sampling in Fock space. There you also have actually a complete characterization of all sampling sets in Bargmann-Fock space, again by density. And we were excited to have another example where you have this almost characterization. Basically, I would say the proof required everything that I have ever learned. So I will say a little bit about the complex analysis part. There is a connection to Gabor frames that I will explain. We used Beurling's technique of weak limits, but somewhere hidden in all these results where you can prove something sharp is notion of spectral invariance. So one version of that is if you have an infinite matrix with given off-diagonal decay, say polynomial off-diagonal decay, and if that matrix is invertible on L2, then the inverse matrix will possess the same type of off-diagonal decay. So this is hidden in many of the sharp results that we could do.
Is this damp course?
They did it for exponential decay, and exponential decay is preserved, but not with the growth, the decay constant. That may change, and you have no control over that. Actually, it would be Jaffar's theorem for polynomial decay, and since then there has been an industry to generalize that. I should also mention there was the 90s Russian school, let's see, Baskakov, Kurbatov, and Gochberg, Wardeman, and third person. So they have independently gotten results for infinite matrices. Okay, so there is a variation that we tried on later, sampling with derivatives. I think there's some interest in that under different names. So now this is a variation. We take function in shift-invariant space so that functions are differentiable, and at every sampling point we not only measure the value of the function but also of a certain number of derivatives. And the number of derivatives I take at x is sort of the multiplicity function mx. So there is a weighted Beurling density. So at every point x, I have m sub x data, and I take the corresponding density. Okay, and in this case, for totally positive function of Gaussian type, there is again an almost characterization of what you can do. So if the weighted Beurling density is strictly greater than 1, then this set plus the multiplicity function forms a sampling set for the shift-invariant space with totally positive generator. And sampling in this case means I take the function and the prescribed number of derivatives, take the L2 norm. This will give an equivalent expression to the L2 norm of f. So that's a variation that was sort of, well, what do you call it, low-hanging fruit. So that's an almost characterization, because as you can imagine, for an arbitrary shift-invariant space where you can sample this is a necessary condition. The same result holds for another function generator, the hyperbolic secant. That's a totally positive function of infinite type, and it also holds for Paley-Wiener space, but there it was sort of folklore, although it wasn't written down anywhere. But so there are several cases where you have an optimal result for sampling with derivatives. I think in more modern terms, people call sampling with derivatives event-based sampling, high dimension, gradient augmented measurements. Well, essentially it amounts to having more information at each sampling point. So let me briefly tell you, say, the core argument before the machinery starts working, and I will explain to you what's behind the sampling theorem when you take a Gaussian generator. So it's for Gaussian generator we have this result, and I would like to explain what's the main complex analysis part that's there. So now we look at integer shifts of the Gaussian, but now with L infinity coefficients. And I look at the set of real zeros of such a function. The claim is the Beurling density of the zero set must be less than or equal to 1. This is where complex analysis comes in. So far, these are, say, real valued functions, shifts of the Gaussian. But the observation is, of course, you can extend to the complex plane. Let's do that. Instead of x, we write x plus iy. If you square that out, you get e to the minus pi x minus k squared. So exactly what you need here. You get the square of I y squared. So that gives an e to the pi y squared. And the mixed term gives you this here. I write that separately because when we now sum over k, you have the terms that do not depend on the summation index. I write them outside. And here, well, you get this modulation of the coefficient. And so the result, if you extend to the complex plane at each level y, you again get a function in the shift-invariant space. Coefficients are related to the original coefficients by modulation, and you get a growth factor. So this is going to be an entire function, differentiable. So it's an entire function. Now this here tells you that you have control over the growth of this entire function. This here remains bounded by the supremum norm of the coefficients. So the growth is basically e to the pi imaginary part of the argument. Second observation, if you have a zero, so suppose that this function vanishes at x. Now let's go to the complex plane and take y to be an integer. If y is an integer, then this is 1. So what's written here is just the original function at x, so it vanishes. So if f vanishes at x, then it vanishes at all complex numbers of the form x plus il. So there's a particular pattern of zeros attached to the real zeros. Okay, now we have the growth and we have a pattern of zeros of the complex extension. So textbook complex analysis tells us how to relate these two. So we can relate the growth of an entire function to the density of zeros, precisely in this form. Here we count the complex zeros in a disk of radius r. So this is an identity. So now let's plug in. here's the growth. You take the logarithm, you get some constant plus pi times y squared. You integrate over a circle of radius r, so the y squared becomes r squared times sinus. So if you integrate that, you get something of the order pi r squared half. Now, if you have if you know the density of zeros, then for sufficiently large r, you know how many zeros are an interval of length 2r, basically this many times r, and now you know how many zeros you add in the complex plane. So if you pursue that, you basically get the number of zeros in the disk of radius lowercase r is basically density of real zeros times the area of the disk. So you divide by little r and integrate, you get that this number here is greater than density minus epsilon r squared half. Compare this here with this here. Well, they must be of the same order, or this is of smaller order, so this implies that the density of the real zero set must be less than or equal to 1. Okay, so density of the real zero set less than or equal to 1. This means if you have a set of density greater than 1, no function in the shift-invariant space generated by Gaussian can vanish unless it's identical 0. So if you have a set of density greater than 1, it's a set of uniqueness for the shift-invariant space. And now morally, if you have set of uniqueness for this larger space with bounded coefficients, then you should get a sampling set for the shift-invariant space with L2 coefficients. That's where all this game with spectral invariance plays a role. But this is the key idea to understand what you have to do. So once you have understood the sampling theorem for the Gaussian, you just multiply these factors. So just briefly, how does that work? So if I multiply both sides with 1 plus 2 pi xi, I get the Gaussian. On the original side, this means I apply this differential operator to the generator and obtain the Gaussian. So this means if I take a linear combination, so if I take a function in the shift-invariant space with generator phi, I apply this differential operator, I get the linear combination of Gaussian. I get something in the shift-invariant space with Gaussian generator. Well, this implies that zeros between any two zeros of this function will be a zero of this function. The zeros of this function and of this function interlace, so the real zero sets have the same density, so same theorem, and then again you can proceed as before. So let's see, I think I have 2 minutes plus 5 minutes discussion.
No, you have 17 minutes altogether. So.
Oh, well then I'll be very happy to tell you about Gabor friends. So now we move to a different type of sampling theorem. Now we go to time-frequency analysis. So I give you a brief dictionary of what we're going to do. So time-frequency shift of a function g by a point in time-frequency space, plane x psi, where we shift by x and modulate by psi. You fix a function g, and then you look at all time-frequency shifts of g by translates that are integer multiples of a parameter alpha, and modulates that are integer multiples of a parameter beta. So time-frequency shifts generated by a certain lattice. The third notion is the short-time Fourier transform, so that's the inner product of f with a fixed time-frequency shift of g, and you look, oops, okay, I'm getting tired. Okay, here. So you make this a function. It's called short time Fourier transform, windowed Fourier transform, because basically you take a window around the point x and then you take Fourier transform. So the question is, when is this set of functions a frame? Okay, so in terms of an inequality, take the inner products. The L2 norm of these inner products should be comparable to the L2 norm of f, this time for all of L2 of R. So this is a question I'm interested in. Now, you notice that this inner product here is just a short time Fourier transform of f with respect to the window G at positions alpha k, beta L. So in other words, the question about Gabor frames is also a sampling theorem, but it's a sampling theorem for the short time Fourier transform. And for each window G that you fix, you get a different sampling theorem. So this is, so that's the question. It's a long history. So this is not cutting edge, but old question. There is a necessary condition. The underlying set is a lattice, parameter alpha, parameter beta. So if you count the number of points per unit square, you find that the density is alpha beta inverse. And the density theorem says that if you have a Gabor frame, then the underlying set has to have density greater than or equal to 1, and you can actually assert that for nice windows you must have strict inequality. So I'll cut. Okay, so what's the connection? This is actually strongly related to the sampling problem in shift-invariant spaces that I discussed before. There is a duality theory for Gabor frames over lattices, and a concrete way to write it down is the following. Goes back to Guido Janssen and the paper of Ron and Shen. And sort of one formulation is normalize beta to be equal 1, then the Gabor set of time frequency shifts for G, alpha and 1, is a frame for L2 if and only if every shifted lattice alpha z is a set of stable sampling for the shift-invariant space with the same window G. The subtlety is this should hold for almost x in 0, 1, and the constants in the sampling inequality should not depend on x. So if you want inequalities, then this holds, so frame, if and only if this holds. Here you have for all x, almost all x simultaneously in all c. So what you see here, this is a function in the shift-invariant space generated by G with coefficient ck, and we sample at x plus alpha j. So Gabor frames on rectangular lattices are closely connected to the question of sampling in shift-invariant spaces. So now that we have some sharp results on sampling in shift-invariant spaces, we just need to translate them, get the result on Gabor frames. The result is the following. So I take totally positive function where the product here is finite and gamma may be 0 or positive. So totally positive function of finite type or totally positive function of Gaussian type. Sorry. That's a more general version that I haven't corrected yet. So for lattices, the corresponding Gabor system is a frame if and only if alpha times beta is less than 1, or alpha beta inverse, the density is greater than 1. So again, here you have just for lattices, a theorem where the necessary condition is also the sufficient condition. There are more general non-uniform versions available, so you can replace one of the lattices by an arbitrary separated set, and well, That's what's left over of that more general version.
You know gamma equal to 0?
Here?
Yes.
Yes.
And in the previous result, it was also the case?
Previous result?
In the case of translation value, you didn't need gamma positive?
I presented two results. One for finite products without Gaussian. There I only stated the uniform case. No, non-uniform, but with maximum gap. When the Gaussian is there, you can work with the Beurling density. So there's a big difference between gamma equals 0 and gamma positive, which density you can use. So the presence of the Gaussian allows you to use the Beurling density.
Yeah, but in lattices, it's the
For lattices, it doesn't matter. So therefore, I stated it for lattices only. So there's an open question. What happens if you take infinite product here? If you read the abstract that I submitted carefully, you will see that I announced something. And yes, we wrote everything down, 12 pages, but it turns out right at the beginning, at the decisive idea, there's something wrong, and at this time we cannot fix it. The adjoint of the complex extension is not the adjoint, the matrix adjoint. So something very trivial got wrong in the beginning, and no matter which limiting procedure we tried, this is still open, and I would like to know that and keep working on it. Perhaps there's somebody in the audience who is interested. But n going to infinity, we don't know how to do that still. So let me give you one more appearance of totally positive functions. The question is, look at the short-time Fourier transform of function g with itself. Except for normalization, that would be the radar ambiguity function. It briefly, implicitly showed up in Holger Rauch's talk. But the question is, for which windows g does the auto short-time Fourier transform or the radar ambiguity function not have any zeros? I personally had a motivation to ask that question coming from certain type of Toeplitz operators. Recently, this condition was needed in the problem about faceless, face retrieval from the spectrogram. So this is a condition that appears there. And so we want to know that. And there is an obvious example. If you take the Gaussian, the short-time Fourier transform of the Gaussian with itself is basically the Gaussian times a phase factor times some normalization constant. So obviously this doesn't have any zeros. And for a long time we thought this is essentially the only examples up to time frequency shifts and whatnot. So we spent an enormous amount of energy to prove that if the ambiguity function does not have any zeros, then it must be the Gaussian. And we have partial results in this direction. Okay, so if g is an even function, then that's true. But then suddenly, turns out, well, the difficulty is there are very few functions for which you can calculate explicitly the ambiguity function. So one example where you can do that easily is the one-sided exponential. Okay, so a friend, very familiar. So we tried, take the convolution of two one-sided exponentials, and it turns out in that case we can still do the calculations, and unless the b is not equal to negative a, you get a zero-free short-time Fourier transform. This example here is also tractable, and you get the short-time Fourier transform without zeros. What you observe is, of course, these are all totally positive functions. It's not clear what's the role of totally positive functions in this game, but all examples we have found of zero-free ambiguity functions are related to totally positive functions. Of course, it can take Fourier transform, then that's just Fourier transform. If you take the Fourier transform of G, that's the same, except that the order is changed, or you can take metaplectic rotations, whatnot. That doesn't change this function, but they're all related to totally positive functions. Why is b not equal negative a excluded? In that case, you get the symmetric exponential, and for even functions, we know that you must get the Gaussian. But it's not at all clear what might happen, what is true, whether this is just a curious accident or not. And so it's an interesting question. So let me just finish. The main message is perhaps totally positive functions rise again to some should I say importance. They were important, and they have been forgotten, and I think there are many interesting problems out there. I mentioned a few where we would like to push to get complete characterization of sampling sets, say for totally positive functions of infinite type. There's this curious question about the ambiguity function, okay, again, old version. But the main thing is sharp results for sampling in shift-invariant spaces for double frames are only known for totally positive functions at this point. So this is quite amazing, and that's why I'm fascinated about that. Okay, so thank you.
Thank you very much. Questions or comments?
I have a question. So you are talking about the shift-invariant space, and in that case, yeah, you have pretty good results in a sense, sometimes optimal, sometimes global. But there are some recent results, I would say, by the Karlheinz and Petrushuk, which can see the more general situation. So based on this equation.
Oh, the Dirichlet spaces.
How could you comment all that stuff? So,
well, okay.
yeah, just briefly.
They basically, well, so you have these spaces associated to the heat equation. There you have projections onto the spectral subspaces, so these correspond to band-limited functions, and they prove that you can sample. So this amounts to existence theorems. And this is a very interesting question that I try to convince people of. You should look at necessary conditions. There are no necessary conditions known. Yet, not
just existence and
yeah. So sampling theorems exist, but you don't know how good they are. There is a theory of necessary density conditions for Hilbert spaces, reproducing kernel Hilbert spaces, where you can formulate a suitable Beurling density and give necessary conditions. I think we have something for the Dirichlet spaces, that you can apply this theory to Dirichlet spaces, but I still cannot guarantee that everything is foolproof in what we did. I'm aware of that work, and there's this gap of understanding. Is there a necessary condition, and what they prove, how close is it? But for their purposes, they just need the existence of sampling sets.
Other questions or comments? I guess people are craving for coffee, and after having a decent cup, there will be plenty of questions in the coffee break. So let's have a coffee break, and thanks for the speaker again.
Thank you.